Welcome to Pre-Calculus. Today we will investigate writing and graphing inverses of polynomial and radical functions, focusing on algebraic techniques to create an inverse and graphical strategies to confirm that a pair of functions are inverses of one another. We'll take a look at two examples that are the polynomial functions first. Our first function is f of n equals negative 2n cubed plus 2. So recall from our previous discussion of writing linear inverses, to write an inverse, I need to switch the domain and the range, which in the case of a function is switch y and in this case n. So just to declutter a little bit, I'm going to call f at n y to begin with. So that's my first step. I'm going to call this original function y equals negative 2n cubed plus 2. And then to write the inverse, I'm going to switch the positions of the y and the n. I'm going to switch the dependent and the independent variables. So what that'll look like for the inverse, we'll be here in the light blue, is n instead of y equals negative 2y instead of n cubed plus 2. So that writes the inverse for me right away. Once I have that written, I do want to solve for y so that it's in a graphable form. We've got some terms to move from the right here, so I'm going to start with this plus 2. A lot of times if you can add or subtract a constant, that's a good place to begin. So I'll subtract 2 from the right. It'll cancel there, show up on the left. Now we've got n minus 2 equals negative 2y cubed. There's another coefficient here, negative 2, so that I want to divide to cancel on the right. I'll also divide the left side, and I'm going to just place that underneath that entire expression n minus 2. At that point, what I've got is n minus 2 over negative 2 equals y to the power of 3. So the only thing left to cancel is the cube. The inverse function of the cube is the cube root. So I'll take the cube root of y cubed, that'll cancel the cube, and that same cube root will appear on the left expression. So at this point, I've got my inverse is y equals the cube root of the fraction n minus 2 divided by negative 2. So that entire fraction's within the cube root radical. Just to indicate that that is the inverse, I'm going to switch over to the f at n notation. So f at, really the inverse of f at n equals the cube root of n minus 2 divided by negative 2. So at that point, we're ready to graph. And for polynomial and radical functions, it's usually most convenient to use a graphing calculator. So let's head over to Desmos and get a table that we can graph from. So we'll type in the original first. We'll call that one f at n, just like it was written. So that's negative 2n to the power of 3, and then add 2. So I'm going to go ahead and get a table for that function first. So it's very much a cube function, cubic function, and negative 2, the value is pretty much off the graph at 18. But then between negative 1 and positive 1, I've got 3 very graphable points, negative 1, 4, 0, 2, 1, 0, and 2, negative 14. I'll record those, and then I'm going to type in the inverse. Now for Desmos, I want to make sure just to call this a different function. So I'm going to call it g of n. Otherwise, it's the same as we wrote for the inverse. It's the cube root of the fraction n minus 2 divided by 2. And make sure that that denominator is negative 2. So that gives the inverse graph And just like I did with that first function, I want to get a table for the inverse so that I can create the graph as well. So some of the values here are irrational. They're decimal values. So -2 has the output of about 1.26. -1 is 1.14. 0, 1. 1 has the output of 0.80 if I round to the hundredth. And 2 has the output of 0. So we're ready to graph. I've recorded those two tables. And let's write those here on our graph. So I need to squeeze down so I have enough room for some tables. Here on the right side is where we'll write those. So the original, we'll put that in the purple color. So we'll call this n. That's my independent variable, and f of n, that's my original function. So that was -218, -1, 4, 0, 2, 1, 0, and 2, -14. Again, just what we saw on Desmos. For the inverse, we'll have this table, n, and that's the inverse of f of n. -2 there was 1.26, -1 was 1.14, 0 was 1, 1 was 0.80, and 2 was at 0. We'll graph these two, but one thing we want to notice is there is a hallmark feature in the tables that would say these are inverses. So if I pick a point from the original 0, 2, I should find the point 2, 0. So those x and y are n and f of n values switched in the table of the inverse. I definitely see that there. See if you can see any other points from the purple table that swap in the blue. Good. So we also have 1, 0 in the original, swapping over to 0, 1 in the inverse. So you can see the inverse relationship in different representations of the two functions. Well, let's graph. So I'm going to graph this purple function first. I can't graph -218, but I can graph -1,4, 0, 2, 1, 0, and then 2, -14 again is off my screen. So I'm going to go ahead and graph that function. Looks like it descends. In fact, let me just really quickly take a glance back at Desmos just to see. So it's always good if you forget what the graph looks like, just take a look at the calculator. So it descends, it has its point of inflection on the y-axis and then descends. And I'll label that f of n. Now we're ready to graph the inverse of f of n. So those are a lot of decimal values, -2, 1, and roughly 1/4. -1 is 1.14, so it's a flat graph. 0, 1, 1.8, so just under 1, and 2, 0. So again, I'm going to graph based on that framework. And we've got a nice graph for the inverse of f of n. So we do see that inverse relationship in the table. I believe we can see it also if we include the identity line. So remember, identity starts in the origin and then goes up by a slope of 1. And recall from our writing and graphing inverses of linear functions, there's two hallmark features. The two inverse functions should intersect on the identity. And we're seeing that intersection with the identity right there, somewhere at about, I don't know, 0.8, 0.8. The other hallmark feature is that if I were to fold over and reflect across the identity, the original should land directly on top of the inverse. Same goes for the inverse. The inverse will land directly on top of the original. And that completes that example. We've got definitely a good pair of inverses that we wrote the equation for, graphed using tables, and then confirmed graphically with those two hallmark features that the original and the inverse, were true inverses. Let's take a look at a second example of polynomial inverse writing. So here's our second example. We'll expand here to see 100%. So this one is h of x equals 2 times quantity 3, x minus 3 quantity to the power of 5. So let's begin by writing the inverse. The nice thing about writing the inverse is that the steps are very predictable. I'm going to start by writing h of x as y to reduce the clutter. So that equals 2 parentheses x minus 3 quantity to the 5th power. And then recall, I'm going to switch the domain and the range, switch x and y. That'll give me x instead of y equals 2 times parentheses y instead of x minus 3 to the power of 5. And then to write that in a graphable form, I want to solve for y. Three things really, the 2, the negative 3, and the power of 5. So usually start outside the parentheses first. So that 2 is multiplied. To undo the multiply, I'm going to divide. And that cancels on the right, shows up on the left. So that my next step is x divided by 2 equals the quantity y minus 3 to the 5th power. So then I got to decide, should I try to cancel the minus 3 or the power of 5? Order of operations says the power of 5 is the overarching operation there. So I'm going to take the 5th root. And that'll cancel the power of 5 on the right. And it will persist over there on the left. So now we've got the 5th root of x divided by 2 equals now just y minus 3. So now I'm ready to add 3 to both sides, cancels on the right. And we've got now the 5th root of fraction x over 2 plus 3 on the outside of that radical equals y. I'll flip it around so that it's more recognizable. Y equals the 5th root of x divided by 2 plus 3. And then to finalize the formal inverse notation, that's in this case the inverse of h of x equals the 5th root of x over 2, x halves plus 3. And that's what I'll box. So we've done the first task, we've written the inverse. Now I want to graph by creating two tables. So again, let's share with Desmos the chance to calculate here. So we'll clear out our previous input and we'll put now in h of x. So we'll just type it the way we saw it. H of x equals, this is the original, 2 times parentheses x minus 3, close parentheses to the power of 5. And I'm going to create a table for that function. So what we see is that starting with -2, the value is incredibly far down off the graph, very much down in quadrant 3, sorry. So I'm going to record at -2 is -6,250. -1's similarly very low, -2,048, 0, -486, 1, -64. Currently, the only graphable point is -2, 2, So I want to include some other values that I can actually graph. So I'm just going to highlight 2 and click enter. So then I see I've got 3, 0. I'll keep going, 4, 2. And that's sufficient for me. So I'm going to record those 6. So note, a lot of times we start with -2 through 2, but you modify that domain if it's not giving you a graphable set of points. Now it's ready for the inverse. So let's call that j of x equals the 5th root. So let's say how we get the 5th root. I'm going to go to the keypad. The square root's there on the main keypad. The 5th root, really the nth root, is hidden in the functions under miscellaneous. And that nth root allows us to input our own index. So we'll put the index of 5, the 5th root of x halves plus 3. So I need to make sure that plus 3 is on the outside of the radical. And that gives me a graph of the inverse. So now I'm ready to create a table for that graph. And that table, by comparison, is very graphable. It is the more horizontal graph. So -2, 2 is on our table, -1, 2.13, 0, 3, 1, 3.87, and then 2, 4. So that's a good list. We'll just stick with that list. And at this point, what we'll do is head back to our note screen to make those tables and graph our functions. So let's squeeze the screen so that we can get some room to write these tables. So we'll put h of x here first. So x, h of x. And remember, we had started with -2 through 2, but extended it to 4 to catch some graphable points. And let's catch those y values. So again, we had to do that because -2 is -6,250. -1 was -2,048. 0 was at -486. So nice points, but ungraphable. Those are down in the basement. -64 is down there as well. Here's where we can start graphing 2, -2, 3, 0, 4, 2. Let's graph that function. So 2, -2's there. 3, 0 looks like the inflection point, and then 4, 2 is on the rise. So here's this function h of x, and we'll label that h of x. Now we're ready to make our table for the inverse of h of x. Now for the inverse, we were good to go with -2 through 2. We didn't have to extend that table at all. There were some irrational values though. So -2, 2 is very rational, but -1, 2.13, 0, 3, 1, 3.87, and 2, 4. So again, we'll graph, just to notice again this relationship between the points on inverse tables. In the original, I had the point 2, -2. So in the inverse table, I've got -2, +2. So you can see those points again switched around. Similarly, I've got 3, 0. I've also got 0, 3. I even see a third one here. So the original has the point 4, 2. The inverse has the point 2, 4. So definitely we can see that inverse relationship within the two tables. All right, so now we're ready to graph the inverse. -2 is at the value of 2. -1 is 2.13, so rising up a bit. 0 is at 3. That's got to be our inflection point. 1, 3.87. And then 2, 4. So we're ready to graph this one. And we'll label that the inverse of h of x. Let's just check graphically that that looks like a good pair of inverses by plotting the identity line. So there's the identity, starts at the origin, slope of 1. And we could go through quadrant 3 as well. And just to remember the two hallmark qualities, the lines of our two function inverse pairs should intersect on the identity. Let's label it the identity as y equals x. And we should also see the reflection. If I were to fold the original over the identity, it would land directly on the inverse. Similarly, if I folded the inverse over the identity, it would land directly on the original. So definitely we can see, in addition to seeing the inverse relationship in the table and the equations, it shows up in the graphs as well. Thank you for joining for these two examples of writing inverse functions of polynomial functions. We'll come back in a moment for two more examples, writing inverses from the radical functions. Thanks for joining. See you soon.